All right, thanks, ladies and gentlemen, and thanks for attending the talks this afternoon too. It should be a pretty exciting set of talks still to go. Thanks to everybody too for introducing the regional geology. It means that it saves me a few minutes in talking too much about the regional geology of Charters Towers. What I'm going to do is change scale a little bit and actually talk about the deformation and mineralization and activation of the main faults that host the ore bodies that make up the Charters Towers deposit. One thing I should say too is a special thanks to Citigold for allowing me to present this data. John McClellan at GEMAX was involved in the modelling, and the previous Charters Towers geologists. There's a lot of data that those guys have collected, so credit must go to those guys as well. One of the things I thought I would remind everybody is that the Charters Towers gold deposit is, even though this diagram is a little bit old, the deposit itself is very much a world-class deposit. It sits up here in the exceptional field. It's got about 6.6 million tonnes was produced from it historically, and the grade is what's phenomenal. You know, you're sitting at well over an ounce per tonne of production over 15, 20 years, right? So it's very, very high grade. It's lots and lots and lots of tonnes, right? You do have, what's almost 7, maybe up to 10 million ounces coming out of this field over the years. It's in good standing. North Queensland has a lot of good gold deposits, including Pajingo and Mount Lation, and these also in the Charters Towers province. So the area is pretty well endowed with gold, and hopefully I can shed a bit of light on that. Just a little bit of a disclaimer that I'm not representing Citigold here. If you want to know more about the Citigold deposit, you have to go to their website and read through their resource and reserve report. But having said that, I did do this work at Charters Towers at Citigold, and I appreciate them for letting me present this data. First, a photo of drill core. This is what a classic sort of intersection in drilling looks like. You've got altered granite in through here, so we're going from shallower to deeper, from left to right. And then all of a sudden you come across these quartz veins. Now, superficially, this doesn't look like a lot of quartz or anything terribly interesting, but this section of quartz was running several hundred grams to the ton. And if you look at it in a bit more detail, you can see that these quartz veins are just absolutely chockers full of little flakes of visible gold. So while the drilling is like, there's a lot of granite for a small bit of quartz, when you do hit the quartz, it's pretty exciting because it's full of gold. In terms of the deposit atlas, I was mentioning to Paul earlier that we've got 350 kilometres of drilling. That doesn't include any of the mine site drilling and grade control drilling, and about 3,200 drill holes. So there is a lot of information from this site, and there's a surprisingly small amount of research that's been done on the Charters Towers deposit itself. I'm not going to go into this in too much detail, other than to say that Charters Towers sits up here. This is a really well-endowed gold province. Mount Lation and Pajingo are just in through here, and Ravenswood over here. The tectonics have been discussed a little bit. All I would like to say, though, is that Charters Towers definitely sits on this predominant east-west trending structural regime. And the east-west trending structures are the ones that host mineralization. There are other north-south trending structures, and I'll show you those in a minute. But that east-west trend, initially extensional, then shortening, that's the major control or concentrating fracture set for the mineralization. All right, let's get into Charters Towers itself. It's hosted within these Siluro-Devonian granites. It's much, much later than the granites. The granites have nothing to do in terms of the magmatic episode, nothing to do with the mineralization. The fractures cut through all the granites. Up here, this is what we refer to as the central area. And where are we talking about today? This is where most of the historical ounces have come from. And then Citigold operated this area down through here, which is about 10 kilometres south, called Warrior. That's been the most recent underground operations. And interestingly, there's another area just south of Warrior called Imperial, and another one up in through here called Milchester. Those two zones are, again, these major east-west trending structures that have been drilled. There's gold there, and basically these remain, for all intents and purposes, unexplored. So there's a huge amount of potential still, even within that small area there. But I'm going to focus in on this area up through here in Central, because that's where we have the most information. Okay, quickly getting into it. The purple lines in through here are the surface expression of the major gold-bearing structures. So if they were to crop out at the surface, if they're east-west trending, they dip to the north. If they're north-south trending, they dip to the east. And that's almost consistent across the field. This is the day-dawn area over here. The yellow are the stoped areas, historically speaking. And the blue in through here are all the underlies and level drives from the historical working. And this was worked back in the early 1900s. The major brilliant structure is this guy here. The bottom of that is about 900 meters below the surface vertically. So it's a long way down. It's about 1.2 kilometers down the length of that structure. So all that stoping there is a lot of material. If we have a look at some of the grades and the ounces that came out, 500,000 ounces at 30 grams per ton, just out of this little zone, 300,000 ounces at 28 grams per ton out here. And then we go to the brilliant, and you can see there's 1.4, probably more like 1.5 million ounces at 27 grams per ton. So it's consistently running an ounce to the ton. Once you get up into here, which is a structurally complicated zone, I'll talk about it in a bit, you start to get larger ounces. That's partly because there's multiple mines operating here, but the grade goes up phenomenally, right? So you're talking about an ounce to the ton on these major north dipping structures. Once you get up into this complicated structural area, the grade jumps up to about 2 ounces to the ton. And I'm going to sort of try to point out a little bit as to why that is. The other important thing is that the gold itself is concentrated within these lobes. It's not as mineralized as what it looks like here. It's very, very patchy. And that's probably the biggest restriction to mining in Charters Towers, and probably why the mine died back in the 1920s or late teens to 1920s. Okay, looking at it simply, we've got three major north dipping structures. We've got the day dawn, we've got the brilliant in the middle, which is the deep one, and then the queen and the sunburst out to the east, again north dipping. And then cutting across these, you've got a series of east dipping, north-south trending structures. These are smaller and tend to be a bit shallower, and then out the back of the structure. So it looks reasonably simple. There's a lot of complications in it, but let's keep it simple just for this talk. All right, in 3D, these are the three main north dipping surfaces, just color coded so I can show you better in the 3D model. This is a view looking down dip, right? So these are big structures and they're pretty continuous as well. Right, when we add on the cross reefs in here in all different colors, you can see that this area becomes very, very structurally complicated, but these are later, younger, shallower dipping structures that I'll talk about. All right, if we look at a long section now, this is the brilliant structure dipping down to 900 meters below the surface. And you can see these stacked form of these east dipping reefs that contain very, very high grade, typically visible gold in through here, sitting above or structurally above the brilliant structure. Right. What do these actually look like when you go underground? This is a typical high grade, massive sulfide section in through here. This is where the gold will sit. The main sulfide minerals that go with gold are pyrite, galena, and sphalerite. Galena and gold, or lead and gold grades, tend to be 1-to-1. You get high grade lead, you get high grade gold. And that's really good for exploration. Once you get out into the structural domain on either side of the shear zone, grades drop off to just a few grams or less than a gram, typically. All this is sericite, chlorite alteration now through here amongst the quartz veining. More importantly, especially for a structural geologist, is just how complicated these structures are. It's not one simple break and one mineralization event. In through here, hopefully you can see there's evidence for lots of deformation events, lots of quartz vein forming events, and in fact there's evidence for multiple sort of injections or crystallization events for the sulfides as well. So there's lots and lots of deformation going on in here. It's not one simple event whatsoever. There's also lots of structural indicators. We know which way these faults are going and we know where the deformation was from, and that's what I want to show you today. Sometimes you get these pyrites broken up and then the gold focused in the fractures and cracks of the pyrite grains, and you can tell from this that the gold's probably been remobilized and crystallized in the fractures associated with pyrite. Okay, so let's keep going because we don't have a huge amount of time. Okay, so in order to try to understand where the gold is on those structures, just from an exploration perspective, for every 7 drill holes that you drill from surface, only about 1 comes back with a mineable grade, right? So it's an extremely expensive exercise to poke around with a drill hole and try to find where these ore zones are. And so people have been trying to work out, well, what are the structural controls on these ore zones? And this is from Peters 1990. And he showed here quite neatly that areas where there's shallow dip in the crosshatch here, which is dips below 45 degrees, there seems to be a bit of a correlation between where the zones of ore are and the shallower dip in the structure. And we sort of thought that this might be a good thing to test. And that model fits this, where you have steeps and then ramps and then steeps on the fault zones. When you shorten this structure, you pop open these dilatant zones and then you open up areas that are suitable for mineralization. All right, so can we use this sort of model, and can we be predictive about where these zones are so that we don't have to keep on drilling? When I was at City Gold, we worked with John McClellan at GEMAX and put together a finite element model to try to go from qualitative to quantitative. We put very, very detailed surfaces in which represent the structures that are hosted to mineralization charters. So we've got the brilliant structure in blue, day dawn in green, and then the blue and the orange and the purple, the blue and the red and the purple are the granite that hosts these structures, right? So we built up this model, and then we're able to deform this model and see where on these structures, where little inflections, bends, kinks, where would open up under dilation and where would be under compression during different regimes of either north-south or northeast dipping, northeast trending shortening, right? So I'm only dealing with the shortening part of the model in this instance. We did 2 models, one with simple structures, the eastern one here, which is the Queen, the middle one, which is the Brilliant, and the western one, which is the Day Dawn. And then we evolved that model into a much more complicated one to include the cross reefs, just so that we could see what happens when we add that confusion into the structural model. Now the results are super interesting, and this is what I wanted to focus on. So the first iterations of the model are north-south directed shortening, and we go through about 2% increments of shortening for each model just to see what happens. In terms of the color coding on these surfaces, the greener the color, the more dilation there is, the bluer the color, the more shortening, compaction or contraction there is on those parts of each of the structures. The orange in here is just for reference. That's the workings or the underground operations on the Day Dawn. So this is a good indication of where the gold is, for example. So in this model, where there's north-south shortening at 2%, we can see the Day Dawn, the Brilliant, and the Queen. The Queen shows some extension and dilation in through here. The Brilliant shows extension and dilation in through here. But the Day Dawn, interestingly, shows compression or shortening in the area where there's gold mineralization, right? So this would suggest to us that, well, maybe the Day Dawn didn't form simultaneously with the mineralization on the Queen or the Brilliant structure, right? So what we're going to do now is increase the amount of shortening. This is a slightly different angle, so we're looking along the Queen, along the Brilliant, and along the Day Dawn here. And you can see again that deflections and variations or roughness in the dip of that Brilliant structure causes areas to become dilatant and areas to become compressive, right? So these are the areas that would likely pop open and concentrate fluid flow and potential precipitation of sulfides, whereas the blue areas, which is most of the Day Dawn, are areas where you wouldn't be getting any dilation at all. So even under 4% shortening, nothing really is happening on the Day Dawn, but the Brilliant is opening up. And part of the reason we think is because the Brilliant dips at a much, much shallower angle. It's like 38 to 40 degrees dip, whereas the Day Dawn is about 45, maybe up to 50 degrees dip in some instances. So the dip angle has a lot to do to whether or not the mineralization will actually occur under this north-south shortening. All right, so let's deform it a little bit more. This is when things start to get very interesting. This is looking at the back of the Brilliant structure in through here under 6% shortening. You can see this green zone in here almost exactly mimics the location of the workings on the Brilliant structure. Again, the Day Dawn and the Queen, there's not a lot of extension or dilation on these two structures, but the Brilliant is really lighting up or opening up to accept sort of fluids. Now, if we pull that green zone out and look at it just by itself, this is what that zone looks like. You can see the historical level drives and underlies in the background. And the model here fit almost precisely with the location of the historical working. Right, so under 6% north-south shortening, the Brilliant really opens up, and you can see that this is probably a likely scenario for precipitation of the minerals on that structure. Right, so we did go further, but things just get a little bit more complicated with respect to the shortening. What we did is we started to swing the shortening direction around to the northeast, and what we found is that the day dawn then starts to pop open, and you start to get dilation and potential mineralization on the day dawn. But interestingly, the Brilliant starts to close off. Right, so just a swing of 45 degrees in the shortening direction, and you change the activation of the structures. Really interesting, especially if you know the structural topology of charts. The other interesting thing is that there's a lot of contraction around these cross reefs at this point. Yeah, I'll get to that in a minute. If we keep on shortening from northeast to southwest, this is when the day dawn really became active. So there's a lot of dilation now occurring on the day dawn structure because it's got a slightly different strike and dip. The Brilliant structure, while there's still dilation there, it's not as significant. But what's really important is that the intersections and the area where you've got this complicated structural zone up in the top of the Brilliant here, that becomes really a concentration for the dilation in the entire model. Right, so this then becomes very active late in the deformation history as we would have it, and that fits with the observations that we see underground. The other interesting thing is, and for another conversation, that intersections between structures are not good for mineralization.
Are you ready to wrap up, Simon?
Yeah, I can wrap up in a second. Okay, so essentially the Brilliant, I guess one of the concluding comments is the Brilliant structure was active pretty much through all of the deformation events. And it's no coincidence that the Brilliant structure is also by far the largest and richest structure on that deposit, right? So it's the one that was under extension for a predominance of all of those deformation scenarios, and it contains the most sulfide mineralization. Okay, so I'll conclude here that what does this mean in terms of exploration and mining? Everything was oriented towards cutting down the number of drill holes, right? So we really wanted to become predictive. Where is the gold? Where are the sulfides? Where are these pods? And by understanding the structural geometry in a lot of detail, not just saying extension is good for mineralization, but actually getting in there and doing the tests and doing the modeling, we were able to then start to pinpoint very high grade intercepts. And in some of these drill holes, we started intercepting new structures. So not only the same structures that they knew were there, we started intercepting new structures, plus every one of those intercepts would have loads of visible gold and things on them. So, you know, one of these drill holes, CT 9004, had 3 intercepts. All of those intercepts had visible gold through them. So by understanding the structural geology, the tectonic regime, going underground, mapping the structures, working out what's going on, you really become predictive rather than reactive in terms of the knowing where the mineralization is. And that was a massive change in our understanding. All right, I'm not going to go through that. So that's a very brief overview of Charters Towers in a split second. Thanks.
Thanks, Simon. Really appreciate it. And we do have some questions for you. And we had reserved a little bit of time to try and catch up on questions and have a bit of a buffer. We've actually already eaten into it, but I would like to do a few questions before we move on to the next section, which will be more sort of stepping away from the regional picture and more localized. Simon, a question for you from Richard Blewett. How confident are you that the finite architecture of the faults, which was used to model the stress, was the same as the incontestable architecture during mineralization?
Okay, so what I showed you there was what I think 6 examples of what was a lot of iterations of that model. There is very little to no doubt. I don't think I have any personal doubt that extension is the trigger for the original formation of those structures. So that wasn't included in that model. Then as you go into shortening, those structures also would have changed geometry a bit. And you cannot really incorporate that change in geometry with that shortening episode. Now, the other aspect of that is all we've got to go by is drilling and a lot of underground working. So I think we've probably got the best model that we can get with the information that we've got without drilling it out to the point where we may as well not do the modeling anymore. So I think in terms of the quality of the structures that were modeled, they were as good as we could absolutely get them. And there are going to be little variations in it. But on the whole, the kinks and inflections and things, I'm pretty confident that we had those in there.